Hi, and welcome to this week's podcast episode of Web3 Compass. This podcast is about Web3, but in order to understand what Web3 is and what Web3 can be, I think it is necessary to understand how Web2, or more generally, how the internet works. So in this week's podcast episode, I have Solution Engineer David Tofan as my guest to explain to us exactly how the internet works and how this relates to Web3. David is my colleague at Cloudflare, but just for the record, a quick disclaimer: any opinions expressed in this episode are solely our own and do not represent the views or opinions of our employer. So enjoy the episode. We are working together at Cloudflare and he is my buddy, which means he helped me during my onboarding process, and furthermore, he's very technical, which is why I'm very happy to welcome on this week's podcast episode David Tofan.
Good evening. Thank you very much, Sebastian. It's a pleasure to finally be on this podcast that I've heard so much about in the last few weeks, months actually. And looking forward to this.
Yeah, you're more than welcome on my show. And I always start with a quick introduction. So who are you and what do you do?
Good question. I'm currently working at Cloudflare, right? Cybersecurity company. For about 2 years now. Feels like forever, but in a fun way and a very exciting way also. I keep learning a lot, but my background is a little different. I was born in Germany, but raised in Spain. Started studying, focusing on nonprofits, political science, social science was my focus, but then quickly gained interest in tech. And started also looking forward to studying more into data science, like getting more into data crunching and data manipulation, which was a lot of fun. But then during university, I had one class that talked about cybersecurity, actually, like data governance as well. How do we secure the data that we're using also for data analytics, for data science? And I found it to be very, very exciting. Heard about Cloudflare, heard about our DNS resolver, public DNS resolver 1.1.1.1, and fell in love. And now I'm here.
Now you're working as a solution engineer. So what can people maybe outside of the tech world imagine under the term solution engineer?
That's a great question. So I am part of the customer-facing team, right? Like who is the pre-sales team in a business, in an organization. So my job is essentially to assist our sales team and assist our prospects or potential customers with anything that is technical questions, technical concerns, demos, dashboard demos, proof of concepts, POCs that we do, trials, and basically everything that is technical. I am the person to ask. If I don't know, I'll be getting back to you with an answer. But everything that is technical for our solutions, how to implement our solutions, how do they work? That's me.
And since quite a while, we today had a meeting with a customer or with a potential customer together, and looking at also the current situation with you sitting now in the Cloudflare office and me here at my home, and we're having this podcast and we are communicating over video. It automatically, I think, leads to the question, how does the internet actually work?
Great question. So the internet is an exciting place, right? Like you and I use it every day without even thinking about it, right? Like how does it work? Why does it work the way it does? And it's pretty exciting to work like also in the space of cybersecurity, because we really have to dive deep into how things work the way that they work, and how can we improve things also in terms of privacy, in terms of security, of course, so that we and also our customers can be happy about it. And I think it's very cool that obviously nowadays we have like this model of where you can be at home, I can be here in the office or at home as well. We have the video call, and in milliseconds or maximum maybe a second, probably like my sound, my image is just reaching your computer. And how all this works is pretty exciting, pretty simple, to be honest, because when we talk about the internet, like we think about everything, right? Like the browser, YouTube, Google, all these like pages that we visit every day, all those apps on our phones like TikTok. But the communication of how it happens, like when you're on your browser, on your laptop, opening Google Chrome or Firefox or Edge, and you type in the URL google.com, there's a lot of things happening in the background. Like when you dissect the URL itself, you have obviously the browser itself like rewriting google.com into this like famous HTTPS, and then double dot slash slash in front, which is like the schema, the way that the communication should happen. Should it be plain text like HTTP only? Should it be encrypted, which is what we want, right? Like HTTPS. Is there like a subdomain or a host name that it redirects to, like a www.google.com? And the google.com part is like the apex, like the domain that you want to visit. But behind that domain, there is an IP address, right? And that IP address, usually you hear always the metaphor of like addresses, like it's similar to a postal office, essentially. Like what is your address, essentially, like your house home address is essentially the IP address of the packets that are going through the internet. And it's not just going from your device straight to Google, right? Like first you have to be connected to your Wi-Fi, to your router. Your router has been given to you by your internet service provider, by Vodafone, Telecom, wherever your ISP is. And then you have also usually a DNS, a domain name system server in the background, which is like the phone book of the internet that looks up, okay, what is actually the address for google.com? What is the IP address? Where does it live? And it doesn't go straight to Google, right? Like first it needs to go through the ISP, through the different cables, through the different other partners of those ISP, the different transit providers, the different networks that ISP is connected to, trying to figure out which is the fastest way to actually reach the servers or like the place where essentially google.com lives. And then get all the way back with the answer, hey, yes, google.com actually lives here, and giving you everything that google.com should give you, right? Like this beautiful logo, the landing page and everything. And it's just very simple, but very like with a lot of history, obviously, in the background, like how it evolved into how it is today, without security or even performance or even privacy in mind, right? Like this all started, as we most of us know, like with ARPANET back in the 60s, like 1960s, like as an educational and military project, but it quickly evolved into so much more. And that's why we are also here today, because it's exciting to see not only where does this all come from, but where it's all going as well, right? Like we have, obviously, with the show Web3 Compass, like Web 3.0, where are we going now from Web 1.0, which was like the very beginning of the internet, like before 2000s, early 2000s, Web 1.0, only read-only, static, very, very bulky, just content like oriented for companies usually. And then we moved into a more like dynamic or interactive environment, which is what we have, what usually we call today the Web 2.0, which is read and write, which is community focused as well, which is like blogs, Twitter, wikis, sharing content, web applications, dynamic, like adding this dynamic part to everything. And then we have the next step, right? Like which is something that you are very interested in as well, which our industry is very interested in as well, and which I'm very curious as well to see where this is all going, the Web 3.0.
Definitely. And before we go deeper into the future of the web, you touched on a lot of points, and I think it's very interesting, this whole process, and also how the current internet works. So if I right now, for example, if I'm searching a website in my browser, you said there's like an IP address which is linked to the, let's say, to the, how do you say it, to the letter name. So Google, for example, where you have the alphabetical characters, of course, and it's linked to the IP address, right?
Yeah, so you don't know that it's linked, right? Like you and your computer have no idea, like that google.com should be IP address so and so, like this address. That's why we need a phone book. We need a place that tells us, hey, where does this actually live? Because there are so many websites also out there and so many IP addresses that it's just too much, and everything is changing so quickly that it's just easier to partially centralize it. It's not very centralized, but partially centralized, basically like this phone book, so that you can quickly just ask essentially like, hey, where does google.com live? And behind google.com on this DNS system, like this phone book that we call it, it essentially says google.com lives on this IP address.
Because we humans cannot remember like the number code, right? But it's much easier to have just a name, google.com, YouTube, Cloudflare, whatever. And it's much easier for us than to have this long IP address, right?
Absolutely. And if we want to go even more technical, like we have the IPv4 version, right? Like the IP addresses that are 192.168.1.1, for example, with 4 octets, which are difficult to remember. But then we have the new, well, not very new, but the IPv6 versions of IP address, which are much longer. So obviously, I think barely anybody in the world has the capacity to remember all those numbers and letters to essentially write those IP addresses down. So yeah, that's why we definitely need a DNS system. And what better DNS resolver, like pointing to a DNS resolver that we want to use that also respects your privacy, right? You often get one assigned by your ISP, your internet service provider. Often, obviously, most people are okay with it. Since we work in cybersecurity, privacy and security is important for us. So we make more conscious decisions about like which ISP are we using, which DNS server are we using, and how are we using it? Because usually DNS also happens in plain text, essentially. But you can also use it over different encryption methods as well. But now we're getting obviously more technical in the aspects of DNS.
Yeah, so very interesting. So if we have now a DNS, and I can imagine it like a phone book, right? So there's a service which matches basically the domain name to the IP address. And this, I imagine it's something like a large register, like a phone book, as we said before, like a phone book. And who can now, for example, access this phone book, and who, for example, is running these DNS services? So can I, for example, now also launch a DNS, or are there certain requirements to fulfill it?
Well, technically speaking, everybody can run their own DNS server. So you can just make a list. There is a way also to just tell your local computer. There's usually like a host file or like an IP config file where you can basically tell it like, hey, this IP address, like this URL, this name, this domain should resolve to this IP address. That's what we usually also see in the industry when we hear about man-in-the-middle attacks or some form of like wire snooping, like people who try to like infiltrate essentially the connection of a public Wi-Fi, for example, that you're connecting to. these bad threat actors, when they intercept your traffic and your connection to the internet, they can essentially tell you, no, don't use this DNS server that is legit, that is pointing you to the right direction, but actually use my DNS server and I reroute you to a malicious website where I want to steal your data or just see what you're doing. So technically speaking, everybody can run their own DNS server, which is literally as easy as just having a server, a computer. I mean, in the end, the server is just a computer where you run a program that accepts like these requests, these DNS requests, and you have the list of DNS servers and domains, basically like a table that says google.com pointing to this IP address, for example. Behind the DNS world itself, so as I mentioned, it's like not centralized, but kind of centralized to like keep like faster, but also a better managed phone book, essentially globally, where we have the 13 main DNS root servers, which are like named after the letters A to M, and they are basically managed by the Internet Corporation for Assigned Names and Numbers, the ICANN and long name. But so basically these 13 like root DNS servers are the ones responsible for essentially like making sure that all the DNS servers in the world, like recursive DNS resolvers or authoritative DNS resolvers, so we have different types of DNS resolvers as well. Some of them can be offered by companies like Cloudflare, for example, where we have Cloudflare as an authoritative DNS server, but also as a recursive DNS resolver and the public DNS resolver 1.1.1 that basically in the background, even though it has like the list cached, like a copy of this root servers, the DNS root servers, it obviously always checks with ICANN and those 13 DNS root DNS servers to make sure that it's always up to date and that it's making sure that it's giving you the appropriate and the right website and the right IP address back.
So can I now say basically that ICANN is more or less in charge, that the phone book is right?
Well, you could potentially say that it administers the DNS, but it definitely also gives a lot of power, because since we are also seeing companies being like offering public DNS resolvers, they are the buffer, right? Like they are the ones in front of those root DNS servers, and they are the ones who can be also a bad actor, right? Like they are usually companies or organizations that are trusted within the industry, that are trusted with also from the ICANN organization, but also within the community, the internet community and the ICANN community, and also having processes in place to prevent any form of abuse or anything like that. It's probably right to say that, ICANN has a lot of power over what's happening with the world of DNS and DNS security. And it's difficult to really say what's really going on there, even though it's a very transparent organization. Like they do have a website, reports, they even publicly also stream like their ceremonies that they do to like rotate keys and so on. They have a report that they always publish, I think every quarter or so. They do.
Yeah, I have to stop you for a second, because you are saying a lot of things, and some people might not know what it has to be with the keys and also ICANN and the domain names. I think it's very interesting, and also the story with the keys. So ICANN basically is in charge to give away domain names, right? So they give them to also other, I think other providers, and there you can buy the domains, right?
So let's maybe start with the fact that ICANN is definitely a powerful organization, right? Like the vision that ICANN has is also like, since they're a nonprofit like partnership actually of like people all over the world, their vision is to like keep the internet stable, secure, interoperable, and they are trying to promote obviously the idea also of like one global internet, right? Like even though, going back to basics, like the internet is made up of many different networks that talk to each other, it's still like one big like web of networks, which we call the internet. And ICANN is responsible for everything that is like DNS, the phone book, the internet's address book. Essentially, they're responsible for this part. And what they try to do with their key signing ceremonies is to provide essentially like a safeguard to keep the internet safe and available. So basically what they do, like they own, like there are seven people, actually seven keys that are physical keys, physical cryptographic keys that are always in secure places. These people have very strict procedures in their life and how they travel and how they work and where they are at any time. Because when these people get together, there's like a special ceremony. I will spare you with the details because there are a lot of details about the ceremony that I would have to also look up. But essentially what they're trying to do is to create a unique pair of public and private root keys to essentially like provide like rotate essentially the keys that are used for the root servers to communicate with the internet, and it essentially provides us with like a validation that these DNS servers are valid, these root DNS servers are still working, and the public private keys that they're using, the public keys obviously that are shared also among the DNS servers, they have not been tampered with, and that these allow you essentially to create also encrypted connections with those root servers. It
sounds a little bit like Lord of the Rings, right? With the seven people secretly all over the globe. And then they come together for this ceremony, and also with the ICANN. It's like a non-profit, multinational stakeholder organization being more or less in charge of the internet, but also very open. So I think this is extremely interesting. And before in my podcast, there was Michael Markovici also, and he had like a where he had, I think, on the Caymans for a time, where he invested in domain names. He also talked about the ICANN and said it's very interesting how they do it. So, but basically, the ICANN is in charge to distribute the domain names, or how can I imagine this?
So the distribution of domain names, it basically oversees the assignment of both IP addresses and domain names, and it has like those domain names are usually like sold by like companies that are like registered as a registrar, right? And those registrars essentially have permission from ICANN, like have a deal with ICANN to essentially sell those domain names to whoever has the money to. It doesn't mean that it's every domain name, right? Like you have to differentiate also between the fact that there are different types of domains, like especially the top level domain or TLD, which is like the right side part of the domain that we usually see, like is it .com, .org, .net, and so on. So all these like top level domains, they're also reserved for specific like organizations, specific situations. And usually a registrar only has also the right to sell specific TLDs. So not everybody can sell a .org or .gov especially. And there have been like a consensus among, well, mostly consensus among the internet community to like establish also like what it means, like this top level domain for specific countries. For example, like you have .de for Germany, you have .es for Spain, and so on. So it's a very interesting industry, and there's a lot going on also with registrars. And yeah, ICANN essentially like runs this like accreditation system, let's say, for those registrars, basically providing them with the ability to sell those domains. They do have a lot of responsibilities, a lot of obligations as well, of course, but it's definitely a very interesting coordination between like ICANN and the registrars, and how they supply essentially like the availability of what can be routed essentially through the internet.
It's extremely interesting. Also, GoDaddy is also famous for buying domains or also selling domains. And now we have basically the icon and we have the domains, and the next thing is the IP address. How or where do I get my IP address from?
So that's the next interesting thing, right? Like ICANN is also the central repository for IP addresses. So it distributes them to essentially network providers. And then you have like those regional organizations like here in Europe, that is called RIPE, RIPE NC, which is like one of the 5 big, like the world is essentially like also coordinated by like 5 regional internet registries, like regional internet registries, yeah. And one of them is essentially RIPE, and RIPE and ICANN work together, obviously, very closely, and through the IP addresses that are assigned to RIPE, RIPE can then give you access or sell access essentially to like specific IP ranges. And as I mentioned, like IP addresses are essentially like postal addresses, you could say. So when you buy a range of IP addresses, which for IPv4, like the standard IP address that you see usually every like if you look at a packet or something, those are very limited, and it's very hard, well, quite hard to get by to buy actually an IPv4 nowadays, especially like bigger ranges. So it's fairly fixed of who has access to which IPv4 addresses nowadays. That's why essentially why we also created, like the internet community actually created IPv6, which is like the new internet protocol for IP addresses, which is like bigger than the IPv4s, because IPv4s are, as I mentioned before, like 4 octets essentially, basically like 192.178.1.1.1, and they use a 32-bit address space, which, like mathematically speaking, basically means that there are like, I think it was 4 billion or something unique addresses for IPv4. But as you can imagine, we already have more than 3-4 billion humans accessing the web, and especially more phones and IoT devices and cars and laptops and so on already accessing the web. Obviously, the community tried to like create as much as of an efficient system with IP addresses as possible, but we essentially ran out of who can use which IPv4 addresses. And that's when we created the 128-bit addresses, which are the IPv6 ones, to get much, much bigger hexadecimal digits, which are like numbers and letters, that that can be also like shortened for representation, and they're like separated by colons. But these essentially are like a new protocol, like a new internet layer protocol that allows us to make use of much more IP addresses rather than just the 4 billion that are very limiting, of course.
Very interesting. And talking about IP addresses, not only a website has an IP address, right? But also I or myself, when I surf in the web, I get also an IP address. And do I get my IP address from my internet service provider? For example, let's say I use Telecom. Does Telecom give me my IP address?
Absolutely. So whenever you're connected to the Wi-Fi, you obviously have a local IP address. That's what I mentioned with like you have, like we tried to optimize obviously the usage of IP addresses. So usually locally speaking, you have like an IP address that is like 192.168.1.1, for example, which is usually like your router or something like that. You have like a local network, and this IP address is reserved also just for local networks. So your Wi-Fi will have 192.168.1. something, and your neighbor might have the same one, and the neighbor across the street might have the same one, and even people from another city might have the same local network, like within their own Wi-Fi, within their own home. But then going out to the internet, right? Since we talked about the internet being a network of networks, when you're going out to the like internet itself, like the network itself, like the big network, you're getting a public IP address, a postal address essentially, so that the internet knows, okay, here is actually Sebastian living, here is where we have to send these things just dedicated to Sebastian. And those IP addresses are usually assigned by your ISP, by your internet service provider, in this case Telecom. They can rotate as well without even telling you. Like it can happen, it happens actually quite a lot, that after a few months or a year or every so often, your ISP changes your local, like your public assigned IP address for your router, like going out to the internet. And when you're a company, usually you want like a static or like a dedicated IP address that is just for you, or that you can use for more than just a year or 2 or 3, to like use it for routing, right? Like if you have to change it all the time or make sure that it's always up to date with the latest IP address, then it can be quite bothersome, obviously. But for you and me, like as a normal internet user, for us, we don't really notice it. We don't really care that much. But yeah, it happens all in the background. It just works, and it allows you to basically connect to the public internet.
Very interesting. And now if I try to understand it and I go the way back, let's say I have like my IP address and I have like my router here in the basement or one router is here in the basement, and then the router is connected, let's say, to the local internet connection. And then we have like, how do you say it in English? Glasfaser?
The fiber optics.
Like the fiber optic. And then there's a fiber optic system. And let's say I want to reach the website of Cloudflare. So the internet service provider, let's say I use, for example, Telecom. The internet service provider sells me my router, and I think the Telecom also has their own infrastructure, right? The fiber cables. But no, not all infrastructure. I think this is where it might get complicated. Let's just imagine like the signal. I want to reach the website of Cloudflare, and the signal goes right here from my computer over the Wi-Fi to my router through the cable, and then it will probably travel to Frankfurt, right? Or to a data center. And then it will be sent probably to the US or
Wherever it's the best way. So I think we have to take a step back here, understand what are the layers that the connection is actually going through, right? Like you have something called the OSI, or Open Systems Interconnection Model, OSI model, which essentially was developed to make sense of how this networking methods work, and how it should go through, and how it should build upon for the internet to actually work. And so they decided on depending if you're talking about the OSI or the TCP/IP layer, you have I will take the 7-layer version now because there's another version of it now, but we have 7 layers. And the first layer, the very first layer, is the physical layer, right? Like you have the physical fiber optic that is basically connecting all the different places. Like from your home, the telecom basically put a fiber optic maybe in your building to connect you through your router, and connect that router to another router that might be maybe a kilometer, maybe 10 kilometers, maybe 20 kilometers away. And that router is then connected to another router, or then to a data center where there's another router. And you have essentially this big web. That's why we call it also the network of networks, right? Like you have this big web of connections going from one router to another by fiber optics, by wireless, by copper cables, which we have a lot also still in Germany. And yeah, essentially what the goal is to create the connection, right? Like first the physical connection, and believe it or not, but I don't remember the exact number, but more than 90% of the entire internet still runs on cable, right? Like, yes, we have satellites, yes, we have wireless and so on, but most part of really a big chunk of the internet still runs on fiber optics or copper, or other types of cable essentially. And you have different types of fiber optic cables and so on, but yeah, let's not go that way. So yeah, how it works is you have obviously first these connections established. You have also the routers talking to each other, basically knowing, okay, I have a routing table that tells me that router A, B, and C are this specific network. Like you have something like a name for that network, right? And you also know that router A is actually connected to router F, and router B is connected to router E, and then also F, telling you essentially that the first router essentially has a shorter connection than the other one to that last router. So you also want to obviously know what's the best or optimized path to also route the packets through the internet. And it's looking at many different things, but usually it's the hops that they call it, how many hops are happening when you're trying to get from A to B to C to D and so on. And when that happens, obviously you're on your computer, you're at the top of the OSI layer, so the 7th layer, which is the application layer, which is the end user layer, where everything that is HTTP based and DNS based. So you have your browser open right now on your laptop. You type into the URL google.com or cloudflare.com. This asks then the DNS server. Obviously, this is already the first step. When you ask for the DNS server, you already have to communicate outside to the DNS server, but let's assume that it just knew, it had it cached, the IP address where does google.com should go. And what your browser does is essentially it goes through the different layers of the syntax layer, the presentation, the session layer, the session itself, if it's a persistent session, for example, and then the transport layer, which is important because this one is deciding if it should be a TCP or UDP connection. meaning TCP for like an acknowledgement that yes, I'm sending you this. I am waiting for acknowledgement that you received this request. Or a UDP, which is usually like when you're streaming something, like for videos or gaming, for example, that you just don't care if the computer, like the end user, like received the packet or not. You just send all the traffic like crazy, essentially. So there are different use cases for using different transport protocols as well. But then you have the network layer, which are the packets itself. So everything is like going like inside you can like kind of like interpret it like a letter box or like a package that you're sending through DHL or Royal Mail or whatever you want to use. So everything is going in and in and in, and you're adding like layers on top. And suddenly you have this packets layer on the network side that says your IP address, that is public, right? And also the IP address to where it should be going. And then after that, you cut it out into like the data link layer, like the frames of that package that basically tell the router or the switch basically at home that, hey, this should be like, it looks obviously at the packets first, at the IP address, like where is it coming from, should it go? And then these frames go through the fiber optic to the next router. And then that router looks at the routing table and says, okay, it has to go to this IP address. What's the fastest way to that IP address? And it essentially usually it asks before, right? Like it already knows by the routing table, okay, this IP address is part of this network that I'm connected to after 2, 3, 4, 5 hops. And this is the fastest way. Like this one has 2 hubs, this one has 4 hubs. Let's take the one with 2 hubs, right? That is faster. And it essentially sends all that to the final destination that it had to go. And there, depending on what there is, but usually it like goes again through fiber optic to the router. It like opens the envelope, opens the package, right? The packets looks at the TCP UDP. Do you need an acknowledgement if it's TCP? It opens the session, it opens the presentation, and then it lands on the application layer again, essentially at the end of the road, going all the way up the OSI model. Obviously, this is a very high level explanation. I'm sure I could do a better job with a better explanation, like with a better example. Another time.
I think you did great. And I think it's also a complex thing, the whole internet structure, and also how it's all built, because there's also something called like the internet backbone, or there are several backbones, right? And what exactly would you say is like your internet backbone?
Well, it's hard to interpret because obviously like companies also say like, hey, I have my own backbone, like my own dedicated like fiber optics routes that I use and I manage. And then you have like the term internet backbone, right? That is like the principal routes, like for large interconnections in the world. You have like these undersea cable map, like submarine cable map, which is really, really cool to see. And essentially like the backbone of the internet is what makes the internet very robust, because it like connects very strategic points, usually like big commercial like companies, educational centers like universities or research centers, governments, military, right? They have like special, in the end they are just fiber optic cables, of course, but they have strategically placed fiber optic cables to like create knots, to create like points where it makes sense to strategically interconnect so that traffic can be routed in a more efficient, in a more smart way. And yeah, I think it just makes sense to like check out the I think it's called the submarine cable map. Yeah, submarinecablemap.com actually. I think it makes sense to like check that out, which shows you like most of the cables around the world, and it shows you like parts of the backbone of what actually runs the internet, because without all these different cables that we have connecting the US with Europe, for example, like London, Dublin to New York usually, then we would have to take other routes, right? And yes, we do have like this redundancy, let's say, quote unquote, going through Africa, Middle East, Asia, over Japan or Australia, even back to US. But that's a long way, and it would definitely degrade your experience of watching a YouTube video, for example. But that's also why content delivery networks caching were invented, right? Like, we want to make it as fast as possible and as best as possible for users to also access different contents, even if the company is like located somewhere else. They usually have like copies of what they offer also in different places. The same way that we have like those 13 root DNS servers, right? They're like located not only in one place, they're like distributed across the world. And this allows us to like create more redundancy, to create fail safes in the end. Like if something fails or there is some kind of disaster happening in one side of the world, we have like other parts that take over. But in the end, the internet is a very, very sensitive thing, and it has been built in a way that we need to fix a lot of things, right? Like it has been built just with research and military in mind, but without performance or without really security really in mind, or privacy, let's say. And there's a lot of work happening, not only from Cloudflare's side, but also from like other companies, a lot of private researchers, as well as a lot of other institutions that are doing a lot of work out there to improve like how the internet should work, how the internet should communicate, like what are new protocols that we could like apply, that we could include into how this OSI layer essentially works. It still all works on this like basic concept of like how it should transverse like the internet, the different packets and frames and so on. Like the OSI layer, I think it's gonna stay here for a while. I don't think it's gonna change a lot in the next 10, 20 years, but who knows? But we definitely see a lot happening in terms of like how it communicates in terms of like this OSI layer, and what can be communicated and what can also be like adapted, that we can improve on in terms of like how HTTP works, how HTTPS works, how cryptography works, what mechanisms you can use to transfer packets even without certain parts of it, or by hiding certain parts of it. And there's like this internet task force, like the Internet Engineering Task Force, the IETF, which has a lot of voluntary standards, like standards that are being implemented and worked on. And it's pretty exciting because they work on a lot of different things, like HTTP3, for example. Quick was a protocol that was developed by this organization. And this is just one small example of how they're trying to make the internet a better place in terms of performance, but also in terms of security and privacy, of course. And yeah, there's just a lot to it. It's difficult to put it all in words.
Very interesting. I thought also about, I recently just watched on Netflix Spotify, the playlist, or I think it's just called the playlist. And it's about like how Spotify was created and their journey. And when they launched their service, they of course need to have like a seamless streaming service of music. And they said, at least in the documentation or in the series, that the internet protocol and I think TCP UDP is too slow for streaming the music. And of course, we also have the CDNs, but I think what Spotify used was also like a peer-to-peer protocol to make like their, at least in the beginning, to make like their music streaming seamless. And when you talked about like the protocols which the internet was, or the protocols on which the internet was created, have to be updated, I thought of this example.
That's actually a great show. I should watch it. I heard a few interesting things. I mean, some people like it, some people don't. Um, but yeah, it's definitely interesting to see how much Spotify has actually contributed also to the industry. Like, it's not only the government, it's not only like research institutions, it's not only Google, Facebook. It's a lot of other companies that we don't really think about sometimes as well, like Spotify, a music audio streaming media service provider that like changed the internet in terms of like the different technologies and protocols that they published. And actually, some of my colleagues also told me that the Spotify engineering blog is very, very exciting, is very, very detailed, very interesting. It's just engineering dot at spotify.com, I think. Yeah. And you can like hear about like what they call like the magic happening behind the scenes, right? Like, what does Spotify R&D, like their engineers, what are they working on? What are they publishing? What are they working in terms of open source as well that you or startups can use? And there are a lot of like, this is another like building block of the internet, right? It's not only DNS and the networks of networks and different ISPs and internet providers, but also the network providers and so on. But it's also like projects, like open source projects that are out there that are helping a lot of companies stay afloat and make things work the way they do. And most often those open source projects are either like financed by companies or by volunteers or like private investors or by donors as well, a lot by donations. And there are many, many different building blocks of like what makes the internet. And it's really hard to really put your finger on like what is actually the internet, what makes it. Like, it's so complex and so diverse that it's very exciting. And I'm sure that my explanations today and everything I've talked to about today, like anybody else, or even at another day, if you asked me like in a week, I would have given you a completely different like explanation and understanding, probably even better than today, because the internet changes, the internet moves, it's a living thing, and everything that makes the internet is also changing very, very rapidly.
Great words. And maybe one final question to wrap up. So what do you think will Web3 or blockchain technology play? And I think Web3 is, of course, not only blockchain technology, but it's a part, in my opinion, and of course, it's a question of definition. In my opinion, blockchain technology is a part of Web3. And maybe to reframe the question, what do you think, or which role do you think will blockchain technology play in the future of the internet?
Great question. I mean, nobody really can predict the future. If somebody could, I imagine they're right now somewhere on an island enjoying life. But yeah, as I mentioned, I think at the very beginning, like we were talking about this transition from Web 1.0, read-only, company-focused, static, to like what we have today, interactive, read-write, community-focused, like Web 2.0, with like all these different applications and so on, and the move to the cloud and so on. And now we're entering the phase of like when do we say that we're actually in the Web 3.0? Because yeah, there are different definitions about it. There are different applications like that are related to Web 3.0. But I think what mostly people agree on is that Web 3.0 is like a more personal, like a more individual focus rather than this community focused part of Web 2.0. And yes, we're talking about like smart like behavior, smart applications, and more individual focused web where the focus is really on giving you, the user, more power over what's happening on the web, over your own data, over how applications are treating your data, and so on. And it's very exciting and it's very interesting, and it sounds pretty good, to be honest, to like, especially working in cybersecurity and being an advocate for privacy, right? Like to hear, okay, there will be a version of the internet that allows me as an individual to take control over how the internet perceives me and how and what I do on the internet. But it sounds also a bit scary, because what does this really entail? Like, what are the mechanisms behind that will allow us that? Because in the end, what doesn't change, like even if we talk about the example of blockchain or like this decentralization of the internet, what doesn't change is how still the packets flow and the traffic flows, right? Like we have still fiber optics, we have still a browser, could be Chrome, could be Firefox, could be Brave, could be another new 3.0 browser. Yeah, in the end, the fundamentals don't change. Like the internet is still working the way it does, and we're still working on improvements and on like making the internet more secure and creating more privacy protocols and more secure protocols and so on. And it's a very moving and living thing, right? And then Web 3.0 are like those applications living on those basics that we talked about, trying to make use of those new protocols and so on to give you that power essentially of how you want to interact with the internet, which gives us power. Yes, I believe that's definitely one way to put it, but it also gives us, let's say, eternity, because in a decentralized system, because it's decentralized, you will have, like, let's take the simple example of, I think Twitter is a good example. Like Twitter can censor like any account or tweet, right? Especially nowadays. And with Web 3.0, like a Twitter Web 3 would essentially be unable to censor or block your account at all, because it's decentralized. Like you put something out there and there will be a copy of it in like 3, 4, 5, 6,000 different places. And it's a bit scary as well, because you're like, which I guess you could argue that it like gives you as an individual more power, but also more responsibility. I guess I would like to put it that way better, because I like that people should take more responsibility also of what they should do, what they do online. And it essentially gives you like this responsibility in terms of like what you do on this decentralized web will be there uncensored and decentralized and potentially forever.
Yeah, very interesting. Let's see how it all plays out. I think there are, of course, very good use cases, but as you said, we have to be careful. We have to be responsible. And I also like working here or at Cloudflare, of course, with the vision to help build a better internet. And yeah, I would say, David, it was a pleasure to be here. Maybe also in the future, we can make another episode about potential cases, how the internet will develop. And yeah, thank you very much for being my guest.
Thank you very much, Sebastian. I really appreciate the opportunity. I'll definitely make sure to give better and clearer and more straightforward examples, especially about the root of the internet, right? It's a
Great.
very complex topic, but I'm happy to have shared a few insights, a few ideas, and hope that people out there listening in are also doing a little bit of research, because the internet is everywhere. We're using it every day, and we definitely should not take it for granted.
That's a great final words. Thank you very much.
Thank you. Take care. Bye-bye.
If you liked the episode, I'm always happy for a thumbs up or a positive recommendation on Spotify, Apple Podcasts, or wherever you listen to the podcast. And besides that, we also have a Web3 Compass Discord channel. The link is in the show notes or in the video description on YouTube. And yeah, have a nice day. Cheers.